Today I'm going to talk about how we estimate power of a statistical test. So first we'll talk a little bit about what power actually is. You may recognize this illustration from the last PowerPoints when we talked about testing means. So what we have here, just to recap, we have a sampling distribution of a null hypothesis. And over here we have a sampling distribution of the alternate hypothesis. Now these have the same shape. I know that my drawing may not show that they have exactly the same shape, but just assume they do. Okay, so they have the same shape, they have the same standard error. That's actually one of the assumptions of many of the tests we do, is that the population standard deviations, meaning their standard errors, are equal. Okay, at any rate. So we talked about how we designate an alpha, right? And then that's a probability of a type 1 error. And then on the other side of that, we have something called beta, which is the probability of a type 2 error. So what power is 1 minus beta. That's what power is. Okay, so let's think about what that would mean. So remember, if we get values in our alternate hypothesis, if they're to the right of a certain value, we are going to reject the null hypothesis. So you can imagine if this area is really, really big, we're going to be more likely to reject the null hypothesis. So imagine if you move this far away over here, then we have lots of power. On the other hand, if we slide it closer over here, we start losing power. And the same thing would be affected by the size of the standard error. So if the standard error increases, right, that increases the width, there's more overlap, meaning less power. All right. So just some things that affect power. Okay, so how do we estimate power? All right, well, I'm going to go through an example of how to do it, but these are the basic steps. We have done a lot of modeling of hypotheses in the last chapter, and we're going to draw on those same skills for this one. So the first step is you sort of model the null hypothesis, and then using an inverse normal distribution calculator, what we can do is we can find the value there that corresponds to alpha. So, you know, for example, well, I'll show you how to do this in just a minute on the computer. So we're going to find a value that corresponds right there. We need to know that because the next step, we're going to model the alternate distribution. All right, and see how if you continue that line up here, that's the dividing line between beta and 1 minus beta, so power is to the right of that line. So if we know what that number is, and we can model our alternate hypothesis somehow, then we can find that area to the right of that value. Okay, so we're going to do all that with a normal distribution in a minute, and then the thing is, you could do that theoretically with any type of distribution. You could do it with a t-distribution. You can do it with a binomial distribution. In fact, with one of the problems in this chapter on power, you are actually going to have to do it with a binomial distribution. So you'll get some practice doing something like this. Okay, so let's move over to this panel. We're going to have an example of calculating power. All right. So when is power useful anyway? I mean, how often do we even care about power? Usually when biologists will have to talk about power when they're asking somebody for money. You know, let's say I'm doing some sort of study and I want to determine if some mean is different from 0 or something like that. So typically what we'll have to do is go to a granting organization and say, well, can you give me X amount of money to run this experiment? one thing that can make a proposal like that really, really compelling is if you have an estimate of power. So typically what a scientist will do is they'll conduct a pilot study first, maybe with a small sample size, and get some sort of estimate of like how much variance there is, and probably what the mean is they're expecting to be. So let's assume we've gone through, we've done some sort of pilot study. For this illustration, because we can't really do this with t-distributions very easily, I'm going to use a known standard deviation. So the standard deviation of whatever we were working on would have to be known. We're going to set it at 10. Now that almost never happens. So usually we have to work with sample estimates of standard deviation, in which case we ideally want to estimate power using t-distributions, not normal distributions. Remember, this is just for illustration. Okay. So we're going to have a known population standard deviation. Now, based on this pilot study we did, we think the mean is about 2. And what we want to be able to do is we want to be able to show that this is different from 0. Okay. All right, so now we're going to tell somebody, give me money, I want to do an experiment. This is what I think. I think the mean is about 2. I'm going to try and do this with 25 data points. And you should give me money. That's sort of what it is. So, well, a reviewer is going to look at that and go, I don't know if 25 is enough. Where's the discussion of power in this proposal? Oh, it's missing. Well, I guess I won't fund it. Okay, so we need to just, talk about power to explain why 25 will be enough. Justify whether or not this granting organization should give us money. So this is what we're going to do. We're going to follow the steps that I showed you over there. So first of all, let's see what the standard error would be if we had 25. All right? So you divide 10 by the square root of 25. I pick 25 because it's easy, because that's 5, right? Square root of 25. So that gives us a standard error of 2. All right, now here's what we're going to be doing. These are the steps we have over there. So here's the null hypothesis with a mean of 0. So its standard error is 2. If that's the case, then the standard error of the alternate hypothesis is also 2. All right, so this is what we think is going to happen. We think that maybe if we're lucky, 2 is like over there, right? And so hopefully there's not too much overlap and we have a lot of power. All right. To find out how much power we actually have, we have to find what this value is. This is alpha. All right. Or if it's a two-tailed test, it would be alpha over 2, wouldn't it? We'll do both just for grins. All right. So we need to know what this critical value is. Then we can model the alternate and figure out what the area to the right of that is. Okay, so I'm going to now go to Lane's calculator for the normal distribution. So I'm going to bring the camera over here to the computer so you guys can see how this is going to work. If you'll bear with me for a minute. Okay, let's see if I can get this screen to work, because I think it's going to be a little more visible. Notice we had some focusing issues last time. Alright, here we go. Hopefully everybody can see that. Okay, so what this is the inverse normal distribution calculator. So not the normal distribution, the inverse normal. Now we need this one because we can put in an area. You see that? Hopefully that's going to be either alpha or alpha over 2. Right now, notice it's set up for a two-tailed test, right? Because if it's a one-tailed test, this is 5%. If it's a two-tailed test, it's half of that, 2.5%. Okay. Right now, I've got the mean set up at 0. That's what the null hypothesis is. But the standard error needs to be changed because we estimated the standard error to be 2 if we're working with 25 subjects, right? Okay, so let me see if I can change that here. All right. Okay, so we'll change this to 2. All right. And to model this, remember we're going to need that score, 3.92. Okay, well right off the bat, you can see that my drawing wasn't that great because 2 is like over here. Remember, that's the mean of the alternate hypothesis. So we're already on some thin ice, so hopefully there's enough area over here to justify this proposal. How much area is over there? Well, we'll have to keep this score, all right? So we're going to need that again, but what we're going to need to adjust here is the 2. Oh, actually, we have to go to the normal distribution calculator. So I'm going to save this. Hold on. Whoops. 3.92. We'll just have to remember it. All right. Normal distribution calculator. Here it is. Okay, because this time we want to find an area, right? So we have the mean of 2, right? And then we need the standard deviation. Remember, that was the standard error, which was also 2. Right, we divided that by, well, we found that based on our sample size. That'll change depending on what the sample size is. And what we need is above alpha, or that critical value that corresponds to alpha over 2. 3.92. Recalculate. Oh, that's not a lot of power, is it? See, if you do that, then the area is only 0.169 after you round it off. So that's the power of this test. Right there, that's the power. It's the area to the right of that cutoff. All right? What does that mean? That means if we do a brand new study and we use 25 data, and we have 25 data points at the end of it, we only have about a 17% chance of getting a statistically significant result. So we're only going to be able to reject the null hypothesis about 16 to 17% of the time. You see how that works? That's not a lot of power. So what would the solution be? Well, we could go through the same procedure and see if a larger sample size would work. So we might go back to our inverse normal. We could try, remember, we're going to try and justify something here. So we would need to calculate a new standard error. So imagine instead of 25 subjects, we had 100 subjects, right? So that would change the standard deviation. I'm sorry, it would change the sample size. I mean, the standard error to 1, because you'd have, remember we had 10 was the population standard deviation. So if you then divide by square root of 100, which is 10, it equals 1. So let's see. So this is with 100. So with 100, notice that our mean is now to the right of that critical value there. So now we can model the alternate hypothesis over here. All right, so we're modeling the alternate hypothesis. That's the mean on this one is 2, remember. But standard deviation now is much smaller. We want the area above 1.96. Okay, so now we've increased the power considerably. See, by increasing the sample size, we've increased the power. We now have about a 52% chance of getting a successful experiment that will allow us to reject the null hypothesis. Okay? Now let's see, I did say I would show you how to do a two-tailed test. So if this had been a this was the two-tailed test. How about the one-tailed test? The only thing that would change for the one-tailed test is we would need 5% here. All right? So that's what we would use. We would use 1.645 on our inverse normal. I'm sorry, on the normal model. Okay.
1.645. Let's see if I can remember that. So we need above 1.645. Okay? Alright. Recalculate. Let's see. What have I done? Oh yeah, this has got to be a 2. Alright. Let's see what the power is. Notice in a one-tailed test, we have more power. Everything else remaining equal. This is again, this illustrates one of the reasons why people get really suspicious if you try and do one-tailed tests, because they know you have a higher chance of rejecting the null hypothesis with the one-tailed test. So notice with this, we have a 64% chance of rejecting the null hypothesis with the one-tailed test. That's the only thing that has changed from the last illustration. Okay, so let's look at a binomial distribution and see what we would do with that. Again, you have a problem like this in this chapter, so I don't want to do too much with this, but essentially you can do a lot of the same thing. So here's kind of the default for, n equals 12. Let's say that's the sample we're working with, and we have a 50% probability. All right. Let's say we're doing a one-tailed test. All right, so we want an alpha over here that's about 5%, right? Well, right now, this is, again, the way it opens up, but if we had picked 9, right, greater than 9, like 10, 11, 12, etc., notice the probability is like 2%. So maybe that's a little more than we really want. So if we did a two-tailed test, let's try 8 and see what happens. Now it's too much. So to err on the side of caution, maybe we need to stick with this. All right. So yeah, it's only 2%, but if we go to 8, right, if we would have done 9, 10, etc., that area is too big. That's more than 5%. Okay. Now, so this is with a probability of 50-50 probability. So if things are completely random, you have an equal chance, like flipping a coin, 50% heads, 50% tails. Now let's say somebody brings me another coin that they think is acting kind of funny, and they claim that it's going to come up heads 80% of the time. How much power would we have to show that? So, I mean, we could run a test, right? Like we could flip it 12 times, flip the coin 12 times, and see, if it is different, from 50-50. How likely are we to get to see that? Because remember, it's a chance thing. If you flip it 12 times, it could fall anywhere on here. Like if it's, for example, if you were to flip a coin 12 times, right? What's the most likely thing that would happen? The most likely thing would be that 6 of the times you would get heads and 6 of the times you would get tails. On the other hand, now, if this thing is doing something like 80% of the time, then we're going to get heads like one of these values up here. It's going to be a different distribution. Let's see if this will even model that. 80%. Yeah, okay. So now you can kind of see if it's really, flawed, like going 80% of the time, notice that you're going to get 10 would be the most likely thing. All right? So how do we find power for a test like this? Okay. So first of all, remember we did this sort of trial and error to figure out where alpha is. So alpha, actually is like over here somewhere, but we can't set this at 8 because we only have 12, so, that's too high. You see what I mean? So this is like the closest we can get to having an alpha of about 5%. All right? Okay, so to err on the side of caution, we're going to now, so this is the null hypothesis. What we're going to do now is we're going to model the alternate hypothesis and see how much area is to the right of 9. So we want 10, 11, 12, and everything else. So remember for this one I said the alternate hypothesis was 0.8, right? Okay, so let's recalculate. All right, there it is. See, this is where our cutoff was. Notice that that area is shaded like 10, 11, 12. So if this coin really is giving us, heads 80% of the time, even with 12 flips, we'd have about, a 60% chance of showing that. All right? So that shows how you can use a binomial calculator to estimate power. But what about a t distribution? Well, this becomes a problem. Notice that when we've been doing these, we've relied on these nice graphs to allow us to estimate where the cutoff is going to be. That becomes difficult with a t distribution because we don't have a graphing program to where we can't always find, critical values. You probably could do it, but it's beyond the scope of this course. I mean, we could use like inverse t distributions and stuff. Instead, Lane has actually provided us with a power calculator here. All right, so I'm just going to show you the way this looks. So you might use this when you're working with a difference between means. Now, the way this particular calculator is set up, it only works if you have equal sample sizes. All right, so you would put whatever you think the estimate between means are. So, for example, let's say we're doing something we've done before. We have like a fertilizer and we want to know if it works. And we think that it makes plants maybe 2 millimeters taller, so not a lot, so a pretty small difference between means. Now, we estimate a standard deviation for the two groups. All right, so we have like a control plot and we have an experimental plot in our pilot study, right? And based on whatever, standard deviation, sample standard deviations we get there, we sort of estimate what we think the standard deviation is. Let's say it's about, 4. That's kind of a lot of standard deviation. Okay, so what I want to know is, let's say I go back in and I do a study where I have 100 plants. How likely am I to reject a null hypothesis? So you have 50 per group, let's say. All right, so 100 plants total. Remember, they have to be equal for this to work. You hit calculate here. That gives you the power of a two-tailed test. So with a really big sample size like this, even with a lot of standard deviation, if the means are 2 millimeters apart, all right, then you have a pretty good chance of rejecting your null hypothesis. With this particular calculator, you can play around with sample size and find out what would work for you. Maybe 100 plants, maybe that's too expensive. It's like really expensive fertilizer, and we can only work with 15 plants in each group. Well, that drops the power considerably. Okay? All right, so this is all you need to know to work problems in the power section. So now try and do those problems. So that's chapter 13.